Hey, welcome everybody into the Wells Tech Garage for today's episode of TechConnect. Today we're going to be talking about all the testing and diagnosing that's related to the DR775 blower motor resistor that you're going to find again on many of your Chevy and GM trucks and SUVs from the late 90s to the early to mid 2000s. If you missed the explanation behind the part, some of the common calls that we get and how to install this thing, make sure to check out the counterpoint video that came out yesterday. Here's a link, follow the link on the screen or in the description of the video below to get that information on how to put this thing in and some of the questions that are revolving around this. Today we are going to be focusing solely on the testing of this system, and behind me sits a wiring diagram for this system, as well as in front of me all of the tools that we're going to be using today for testing. To properly test the first time accurately for the system, we're going to want a couple different tools. Voltmeter or DVOM that's able to do resistance and voltage. We're going to want an amp clamp, and then we're going to want a test light and what we'll call a super test light. I'll get to this guy in just a few minutes here. So the testing procedure for this is going to depend on the failure that happens for your blower motor resistor. So before we get to failures, let's just really quickly go over circuit operation and how this entire circuit functions on the vehicle. We'll start at the top, that's where I like to start with diagrams, and work our way to the bottom to ground. So we're going to start with this 25 amp fuse and this 30 amp fuse. These are both going to be powering up our blower motor at one point or another. The 25 amp fuse is going to be powering speeds 1, 2, 3, and 4. That 25 amp fuse will be powering a relay coil for high speed, but high speed blower motor operation will be powered by this 30 amp fuse. So let's trace it out. 25 amp fuse feeds power through, let's say we're on speed 3. We're going to go down through the resistor element on speed 3, through the resistor element on speed 4. We're running these resistors in series, dropping the speed of our blower motor by resisting the electricity that's able to get to here by going through 2 resistors. And then through the relay, which is going to be in a normally in this position right here, to our motor, which comes up through a splice back to ground. Everything you see in this blue square right here is located internally of the DR775 resistor. So if this relay were to go bad in here, this relay that's sitting normally in this position, if that were to go bad, this entire resistor would need to be replaced. Let's look at another scenario. Let's say we're going on speed number 1. So our arrow goes to here. We flow power down through resistor element 1, through resistor element 2, through resistor element 3, and then through resistor element 4. This is dropping the most amount of electricity going to our motor, therefore our motor spins the slowest as it gets to it. Now let's say we're going on high. We turn the switch to high, our switch goes here. We send our power to the control side of the relay here. It brings our little switch contact closed inside of the relay. Now we're feeding power directly from this 30 amp fuse directly into our blower motor, which then feeds directly to ground. This is going to give us the most power, the most flow from our blower motor. Now, in a wiring diagram on this circuit, grab it out of the truck, it is possible if this relay were to fail, if we were to get a situation that would cause this relay to stick in this position, if our relay were to stick in the high position, it is possible that this blower motor were to run after the key has been shut off on this vehicle. This fuse right here, 30 amp fuse, is hot at all times, okay? It's really important to note on these trucks. This fuse, hot at all times, not controlled by the ignition switch like this fuse is. So, we have the internal relay of the resistor. If it were to get hot and melt itself in this position, on high speed, our blower motor would run at all times, creating a massive parasitic draw, killing our battery on this vehicle. So keep that in mind if you're diagnosing one of these that's stuck on high. It's very possible that it needs a blower motor resistor, but it's also possible there's other things wrong in the circuit. We'll get to that and why that is in just a second. Let's start out with some bench testing really quickly of a resistor. These are specs that we provide online. You go to wellsve.com and you search by either DR775 or you put in your vehicle information and you'll come up with this sales drawing that you see here. We include a nice wiring diagram. We include some nice pictures, color pictures of this thing, and we include specs for resistance so we can bench test this resistor. So what we're going to do is we're going to take one lead of our meter and we're going to go on the red terminal that goes to the blower motor. This would be blower motor positive. This is our red wire here. And then we're going to go through each speed of this thing. So we're going to start at low speed, and I'm not going to do them all. I'm just going to do a handful of them here just to show you guys. So I'm going to start with pin B, and they are all labeled right inside of this connector, making it very easy for ohm testing. So I'm going to go pin B. We should see, this should be our most resistance. It should be between 2.62 and 3.77. And there we're sitting at 3.2 to 3.3 ohms of resistance. Looks good. We'll set that there. And let's just go to pin C. That's going to be our medium 3 setting. So just before high, this is going to be second from highest, pin C. We should see a resistance reading of 0.16 to 0.23. And this, again, was the resistor that came out of the vehicle. This resistor was made in 2008, so it has been in there for quite a long time. Let's see what that spec is. So we got 0.2 ohms of resistance on this one. And according to our spec, we should be between 0.16 and 0.23. So we are in spec on our resistor. Our resistor is functioning fine, and it was before we put the new one in the counterpoint video as well. This one was not having issues. So you can always do a static resistance check on your resistor if you're having issues. Okay? So that's one of the tests that's very easy to do, and we give you all of the specs right on our website. But let's take a couple different scenarios really quickly and talk about them before we get into the testing. Let's talk about two. Let's talk about complaints. Let's talk about a failure from a customer that says, let's say the speed 1, 2, and 3 are not functioning. Okay? If speeds 1, 2, and 3 are not functioning, what could it possibly be? If we look at a diagram, either one of these, any one of these resistor elements could go bad. Let's say it's just resistor element 3 that went open. For whatever reason, it's gone open. It's not able to flow any power across this resistor element right here on speed 3. That's also going to affect speeds 1 and 2, because if we put our switch here and we flow power through this resistor element, through speed 2's resistor element, we have to get through speed 3's resistor element in order to get to our blower motor eventually. We're not able to do that. So a resistor that's failing on one resistor element will take out multiple speeds. But what if the customer complaint was only that the speed 3 was out? Speeds 1, 2, 4, and high were all functioning perfectly fine. Only speed 3 was out. That means that everything after this splice right here, this splice here, has to be okay. Because we're able to function for 1 and 2, that leaves us with the only option for speed 3 to be out would be somewhere between right here, the connection that the switch makes inside of the switch, between there, this wire, and this splice right here. Somewhere in there is the only problem. So a switch or the top part of this connection or this connected and wires in between there. It can't be anything down in the resistor element. So keep that kind of stuff in mind when you're diagnosing these things. Single speed failure, more often than not, leads to a switch issue, and multiple speed failure, more than often than not, leads to a resistor issue. But in order to diagnose this and fix it right the first time without guessing, we have to do some testing. Now, when I test, I like to test in the most efficient way possible. I like to not waste any time. I don't like crawling around on my back under the dash. So I want to do the simplest of testing and get as much information as quickly as possible. That's where we're going to start with the test light. What we're going to do is we're going to unplug the blower motor. We're going to turn the key on, and we're going to take the test light across the two connections at the blower motor, just substituting the load like so. We're going to turn the switch into each of its positions from off all the way to high, and we should see the test light light up. If the test light doesn't light up in one position, then we know that we have an issue somewhere in this circuit. But this is able to tell us, hopefully, that we have current flowing through the circuit and that we have power and ground. So instead of using a voltmeter that's only able to check voltage, we're actually able to check current. So let's take this test light and see what we got. Okay, so for our test with our test light, we got to make sure that we have the key turned on. And we're going to unplug the blower motor. And we're going to just substitute the test light for the circuit's load. And right now I have the blower motor turned off. We'll go ahead, we'll insert the test light into here. And let's see if I can hold this. And speed 1, speed 2, speed 3, speed 4, and high speed. And then we work back. 4, 3, 2, 1, off. Okay, so as you saw, the test light didn't really change in intensity on any of the different speeds. And that's because a test light is not a good load substitute in a circuit that's intended for a high load. A blower motor draws a lot of amperage. A test light, not so much. We're looking at about a 1/4 amp or so on this thing. So we're not really going to see an intensity change because on speed 1, it's enough to light up the test light, and on speed 5 or high, it's enough to light up the test light. We need to substitute an adequate load into the system. Now, we could grab a different blower motor, but a blower motor is not going to give us any sort of visual representation. You can't count the RPM on the blower motor. But what we can see is different intensities of light. So I'm going to use our super test light here. This is our 6.5 amp load test light. This is just a sealed beam headlight. Draws 6.5 amps. Plug this in place of our load. So we're going to take red and black, unplug the blower motor, plug this in, change each speed, and see what we got. So let's take a look. Okay, so again, this isn't a test light, it's just a headlight bulb, but it's going to act as our, we'll call it the adequate load in the circuit here. So I'm going to get it wired up, and then I'll shut this light off so we can watch as this thing goes. So right now, the blower motor is currently turned off. Let's see if we can get these to stay in here. Perfect. Turn off the light. Okay, so speed 1. A little bit. Speed 2, 3, 4, and 5. Now that I blinded everybody out, we can definitely see a difference. And let's turn the light back on so the camera doesn't freak out. Let's just show you guys again. Okay, so a definite difference in our test lights. All right, so we definitely saw a difference here. You know, speed 1, very dim. Speed 5, or high speed, nice and bright. Definite difference on the headlight test light on this one. So that tells us a ton of information. Remember, we're focused here on efficient diagnostics. So that tells me that our resistor is functioning, that tells me we're able to flow power, that tells me this fuse is okay, this fuse is okay, our wiring is okay, we're able to do what it's supposed to do. The system right now is checking out. We don't know the exact perfect specifics. We don't know if it's exactly the right amount of voltage traveling through the system. We don't know every detail of information, but we have a general idea that on speed 1, we have a small amount of energy ending up here, giving us a very dim headlight. And on speed 2, it gets a little brighter. Speed 3, a little bit brighter. Speed 4, a little brighter, a little more energy. And speed 5, it gets to be the brightest or the most amount of energy flowing to our blower motor at that point. So we know the resistor is doing what it's supposed to. We know this relay is doing what it's supposed to. We know all of our fuses and power wires are doing what they're supposed to. But what happens if this is an intermittent issue? What happens if we took the connector off yesterday on this resistor and we saw a melted connection? What happens then? You know, blower motors and blower motor circuits are very common, probably the most common to have melted connectors. Why are they melting? Well, there's high amperage draw. High amperage equals heat. You know, the more current we have, the more heat that we have if there's any sort of resistance in the circuit. So we want to be able to find a way to check out what our amperage reading is. The best way, get the circuit fired up, put an amp clamp around one of the wires going to our blower motor. And now you're not going to be able to go out to your service information usually and find a spec on this. What should this motor pull? There's probably not a published spec. What we like to go off of is a rule of thumb of half of the circuit protection on high speed. So circuit protection here on high speed is 30 amps. I want this motor to pull under half of 30 amps, so under 15 amps on high speed. So why don't we grab our meter and grab our amp clamp, and let's take a look at what this motor runs on each speed. Okay, so now for the current test for our blower motor, we set our meter up on volts, and then we get our amp clamp out, and always, even though we're using an amp clamp, guys, we're still working on voltage. This amp clamp converts amperage into a voltage reading for our meter to show us, and then we have to move our decimal point always. We're on the 1 millivolt equals 10 milliamp scale, so we're going to have to move our decimal point one place. We're going to put this in just like we would any other volt testing, like so. Put it around one of our leads for our blower motor, and we just got to plug this thing back in. Okay, so plugged in, speed 1, and again we got to move our decimal point, so we're reading 2.1 amps on low, or speed 1, speed 2, 3.9 or so, 3, about 6 amps, 4, about 7.5 amps, and 5. Hey, 10.5 amps, that's not so bad. Let's go ahead and shut it back off, and let's do one more run. Let's just zero this thing out one more time and make sure that we're still accurate. Speed 1, speed 2, speed 3, speed 4, and high speed. It's definitely under that 15 amp mark. All right. Okay, so you saw as we went up in speed, we started at roughly, what was that, about 2 amps or so on low, all the way up to the 11 or 12 amp mark on high speed. Still under half of our 30 amps, still under 15 amps. This blower motor seems like it's doing its job, and it does not have any sort of internal resistance. It does not have bearings that are sticking, causing a higher amperage draw. Everything is good, and we kind of figured that because our connector's not melted, we're not running into issues on this thing. So if you are running into connector melting, if you've replaced the blower motor, or if the blower motor resistor has failed, it's always a good idea, always, to check the current draw on the blower motor itself, because blower motors are known to kill off these resistors. Okay, so we got one last test that I want to talk about today, and that is voltage dropping this system. Because I want to be efficient, because I want to know what my switch condition is. Say my blower motor was drawing 18, 20, 22 amps. It was drawing excessive current through our system. I want to be able to verify that the switch is okay, but I don't want to do a ton of work. I don't want to pull the dash apart. I don't want to have to pull the whole HVAC module out. I don't want to have to do any of that work. What could we do instead? We can voltage drop. Now we could start at battery positive, and we could go all the way. Remember, a voltage drop test is testing one leg of the circuit while it's in operation. So we're going to test with the key on, blower motor running. We're going to have one lead of the meter on battery positive or on our fuse. And then the other lead we're going to put at this connector. This connector is pretty easy to get to on the resistor. We looked at it yesterday. It's the one that plugs into here. And we're going to voltage drop across our fuse, across this wire that goes to our switch, through our switch to each of these components. Now we should probably see some voltage drop in this system. It's just going to be the way it works. We should see some voltage drop because we are moving quite a bit of current through here. That current creates heat. We will see some voltage drop, but I'm not looking to see 2 volts, 3 volts of drop across this thing. You know, I'm looking to see maybe a couple 100 millivolts of drop across this thing. So I think for ease of access on this, we'll just test this circuit. We're going to start at the fuse here. And again, the circuit needs to be intact, and we're going to turn it on, and we'll measure at the connector going into the, we'll back probe at the connector going into the resistor for each speed, and let's check out what the drop is. Now, if we had excessive drop, I'd be pulling out the switch to look at it, but let's go take a look, and let's see what we've got for a voltage drop reading on this thing. All right, let's do it. Okay, so time for our voltage drop test. We're going to take the red lead and put it on the most positive side of our circuit. So we're going to go right to our fuse like this. And then our black lead, we're going to back probe into each of the spots on this resistor here. We're going to go on the input side. We should see a voltage drop before I turn this on. We'll go speed 1. About 150 or so millivolts on the yellow wire. Then we go speed 2, that's going to be on the tan wire. Oh, let's see if we can find the, about 149 or so. Sorry, take that back, 300. Make sure I'm on the right speed here. About 300 millivolts or so. Then we'll go light blue wire for speed 3. There we go, speed 3, about 450 or so millivolt drop. Speed 4 is going to be a purple wire. So you can find it here, about 560 millivolts, so just over half a volt drop on speed 4. And then speed 5. Speed 5 is showing 15 millivolts. So the reason why speed 5 is showing only 15 millivolts on here is because in speed 5, that 25 amp fuse that we're tapped into right now isn't actually drawing any current. So that 15 millivolts on here is accurate because our current draw on the circuit on fuse 25 where we're hooked in has actually dramatically decreased to there. All that current that's going through there now is just to power up the relay coil. The main current for the blower motor is coming through fuse 30, the 30 amp fuse for the front HVAC high speed. So that's why our voltage drop is much less on number 5 because of where we're starting the circuit. Okay, so we did see a little bit higher than I expected to see voltage drop. You know, that 500 millivolt mark was a little bit higher than I anticipated on high speed. But I don't think at this point we're looking at pulling the switch apart. This system is functioning. We don't have melted connectors. I'm not worried about the switch. If I was dropping 2 volts, 3 volts a drop across this switch, I'd be pulling this thing apart to look at that connector, see about putting in a new switch and new connector. Now, hopefully in the near future here, guys, we will have a video out showing replacing one of these connectors. I got another vehicle that will be coming in shortly here that we're going to actually have to replace this connector because they melted it. We're going to do a voltage drop across that connector and see what that one comes out to be, but I would expect that to be significantly higher than the 500 millivolts that we're dropping here. So at this point, we're not pulling the switch apart. I don't think it's necessary. 500 millivolts on high speed seems to be kind of the common where we're going to be sitting for this. What do you guys think? Have you run into about 500 millivolts drop? Does that sound good to you guys? Have you run into lower, higher? I would think we're going to see differing voltage drops on differing loads, you know, different blower motors, bigger blower motor, drawing more amperage, creating more heat, therefore a higher voltage drop. So I think that's going to be it. I think we have now verified the entire circuit in the most efficient way possible. We loaded it. We checked it out down here. We knew that it's able to pass current. We were able to verify every piece of the circuit and understand how and why it functions. I think that's about it. If you're looking for how to install the part, make sure to check out the counterpoint video. Today, again, we were just focused on the testing of the part of the DR775. So I think that's about it. If you guys liked what you saw, please give us a thumbs up. Please subscribe if you already haven't. Make sure to share the video. Check us out on social media, Facebook, LinkedIn, Instagram, and Twitter. We're on all of them. Search for Wells Vehicle Electronics or follow the links that are sitting below in the description of this video. I think that's it. We go live with the next live training class on February 1st, so make sure to join us for that. Until then, guys, I hope everybody has a great day, and happy wrenching, everyone. Thank you.